Hi, I'm Andy Keep. You may know me as one of the maintainers of Shea Scheme. I'm also someone who's worked a lot with the Nanopass framework. In fact, it was the focus of my dissertation, rewriting Shea Scheme to use the Nanopass framework. Today, I'm going to talk a little bit about writing tools like the Nanopass framework using the Nanopass framework. And before I begin, I just wanted to say thank you to the ELS organizing committee for inviting me to speak and for putting all of this together despite the challenging times. So thanks very much. It's really very much appreciated. To give a little background to begin with, the Nanopass framework, if you aren't familiar with it, is an embedded domain-specific language for creating compilers that focuses on creating single-purpose passes and precise intermediate representations. The DSL aims to minimize boilerplate, and the resulting compilers are easier to understand and maintain. At least that is the goal. So we have two forms in the language, define language and define pass. Define language is used to specify the grammar of our intermediate languages, and to the point of being able to create things with less boilerplate. You can create new languages by extending an existing language. And so you don't have to write out the full text of every language. And this becomes important when you start to have 10, 15, 20 intermediate representations, and each one of them is really just a small change on the previous one. Define pass is used to specify our passes, which operate over an input and produce an output. Now, of course, in general, we will use these with over two languages. We'll have an input language and an output language that may or may not be the same. And we'll use them for transforming the input into the output. But for particularly for things like the first pass in the compiler, we often don't have an intermediate representation to begin with. We have to parse to get our intermediate representation. And for the last pass, we often have no output language. So we're often going from an intermediate representation to whatever our final target is, whether it's machine code, assembly code, another programming language like C or something like that. And so we can have passes that only have a language on one side. And we can also have passes that have no language at all, but this essentially is just a function. It's just the syntax nicely degrades to this. To walk through a little bit of an example, this is what a language definition looks like in the Nanopass framework. We have a name for the language that we're creating. We have a set of terminals, and each terminal has a name. We expect for our terminals that there will be a predicate that matches that name in the environment. So here we have a terminal name symbol. We expect there to be a symbol question mark in the environment. And similarly, datum question mark and primitive question mark. And then we have one or more meta variables that represent the language, or represent the non-terminal rather, in the productions of the language. Then we also have non-terminal, one or more non-terminal expressions. Each one of them has a name, as well as a set of meta variables. And then in each production here, we can use sort of this S expression syntax for defining our productions. And the first position here is treated a little bit specially. We can have something that is not a meta variable, and we will treat that as a keyword. And so it won't really be part of the underlying pattern, but it will be something that's used when matching both to bring in S expression syntax into this, into our underlying representation. It'll also be used when we're doing pattern matching in our passes and things like that, and we'll see that in a moment. But it's important to note that this is the only position in the language where we can have these keywords, just in this start of our one of our productions. So we can also extend a language, create a new language by extending the first one. So we have this extra extends clause when we do that. We tell it which language we're extending from. Here we're extending from L1. And then we have a slightly different syntax. So now we have a minus part of our syntax here that tells the system that we're removing these productions from this non-terminal. Here we're moving one-armed if, let, rect, and lambda. And then we also have a plus syntax for adding productions. Here we're adding a simplified let, rect, and lambda where we can only have one expression in the body. We can write a simple pass over this language. So for lack of a better name, we're going to call this pass simplify. It's going to take L1 as our input. It will bind the variable IR to whatever its input is. We could pass additional values in if the pass needed additional values. And then we're going to produce one language form as an L2 language form. And the empty parentheses after here are a place to allow you to specify if you'd like to return more than one value. So that gives you some space to do that. Then we have a set of one or more processors in the language. Here we have our processor for processing the L1 expression into an L2 expression. It sort of has a similar syntax to our defined pass where we have a name, a colon, the input type, and the output type. Note this name, while we used expr here as the name, it doesn't have to be expr. Within each of our processors, we have a set of clauses. Each one of these clauses is composed of a pattern match, and we can have nested patterns within here. It's important to note that while this looks like an S expression matcher, it's actually matching an underlying record that represents this. And it's just that we have the programmer can speak to this in terms of S expressions. While we aren't doing an interior match of any interior form, we are doing using a catamorphism here. That's what this syntax represents, where we have brackets within our escaped section. So this will look for a processor that knows how to convert expressions into expressions. In this case, we only have the one processor, and so it'll use this processor that we've written, but it will basically convert the L1 expression into an L2 expression. Finally, we have some construction of an output term. You'll notice that we use this quasi-quote syntax. Again, we're not really constructing a list here. We're constructing a record. In this case, we're constructing two records, one that represents the lambda expression and one that represents the begin, that is the body of that lambda expression. Now, we might want to be a little bit more careful here. If body star is an empty list, there's no need for us to add the begin, and we might want to avoid it because we might want to avoid creating unnecessarily extra records, but you can get the idea here. And we might have a more complicated language with many more types of non-terminals, and the catamorphism syntax is smart enough to figure those out, and it potentially will also even generate processors for us if we haven't given it processors for everything. So that gives you sort of the ref overview of the Nanopass framework and sort of how it works. As I mentioned, we have two main forms in the language. Defined language is our method for defined languages, but we quickly found we needed to have other things. So language arrow S expression allows us to retrieve the full definition for a language. You might wonder why you want this. Obviously, you wrote in your source code what the definition of the language was, but what you find is that as you have more and more extensions to a language, it can be harder and harder to keep track of exactly what that language looks like. And so language arrow S expression, you give it a language name and it will give you back the syntax that would be used to define that language as if it was defined as a full language. We also have the dual of this, which is diff languages. It turns out that sometimes you are writing a pass and you have an input language and an output language, and you don't have a direct comparison between the two of them. And so diff languages provides a way for you to see what has changed in the language and get a feel for what you need to address in your pass. Prune language actually goes through a language and figures out non-terminals and terminals that may have been, that are unconnected. So you'll never have a non-terminal or a terminal of that kind in the language. It turns out this comes up occasionally as you're extending languages. You might leave behind a non-terminal production that you didn't realize you had, especially as these things evolve. Sometimes you've added a production and you forgot to remove it in some later pass. We also have some tools that we've written to help as we're trying to figure out the performance of our passes and our compilers that we generate out of this. define language node counter. It gives us a function for counting the number of nodes in a language expression. So you might define this and stick it in your compiler before the pass to figure out how large the input to your pass is. Maybe stick one at the output to figure out how big the output for your pass is. That can give you an idea of how much expansion is happening within that pass. It can also give you an idea of what the time is like based on how many nodes are in the system or how many nodes are in the input for it. And so you can get some experimental results on figuring out like what the performance, sort of the big O of your pass is. Now, define language actually defines a parser and an unparser, or at least it originally did. What we found was that we oftentimes didn't need the parser. And so we separated out into a separate piece of syntax. Define parser allows you to define a new parser with a name for that parser function and the language that you're parsing. This basically gives you a way to take a concrete S expression, turn it into a language form that you can then operate on with the rest of the Nanopass system. And even though we do still produce unparsers from the language, we also have define unparser, which allows you to define an unparser for the language, partially just to have sort of both sides of this. And we've also done other sort of one-off things. It turns out that define language node counter is oftentimes not as precise as you want it to be. We made certain decisions when we wrote that. We don't count, I think we don't count terminals in the node count, but maybe sometimes you want to. Particularly if you have a list of terminals, you may want to count that list as part of your node structure. And you sort of want a way to be able to write, we've written some one-off bits and pieces, but you sort of want a more general way to write more of these kinds of tools. Define passes evolved in similar ways. One of the first things we found we wanted was with output language. This gives us a way to generate language forms outside of a pass. Nanopass case gives us a way to do matching of terms outside of a pass. And so these together can, basically have the two parts of the functionality for define pass. But it turns out they're useful to have separate from define pass. Echo define pass is a debugging tool. It gives us a way to have define pass produce the syntax that it's going to generate as part of its expansion. It's actually not quite what you want. It's sort of a proxy for figuring out what boilerplate define pass is going to generate for you. In some cases, what you really want to know is what that boilerplate is, and the actual syntax can be a little bit tricky to read. But it has been useful for us over the years in trying to figure out where our sort of smart auto generation of things has gone awry for us. Trace define pass is a way of tracing the inputs and outputs from a pass, so you can see when your compiler is running, what does the input look like and what does the output look like. In both the case of echo and trace, these can also be used with our processors so that you can have the processor echo the syntax it's going to generate for it, so you can see the boilerplate just for that pass as it's generated out, or just for that processor it's generated out. And trace allows you to trace just the inputs and the outputs for that particular processor. We also have some things that are used for looking up in the syntactic environment and figuring out information about the pass. So pass input parser, it turns out it's useful if you're writing sort of little coarse compiler style compilers. You'd like to be able to start that compiler maybe in the middle as a way of doing some debugging. Pass input parser gives you an easy way to look up what the input language parser is for a given pass. And similarly, pass output unparser gives you a way of looking up what the unparser is so that you can get an S expression back out of the pass pretty easily. And over the years, I've had requests for other things that I have never gotten around to implementing. But some interesting things in particular, I think, define extended pass, which would be a way to extend an existing pass to give you a new pass, maybe because you have an extended language or because you had some functionality you had implemented before, you don't want to rewrite it, and you just want to extend beyond some existing piece. you can imagine this being useful in a compiler course, and it can also be useful when you're writing things like live variable analysis, where you have a couple of different places in the compiler that you do live variable analysis. They're very similar but slightly different, whether you're dealing with frame variables or register variables. I've also wanted to have some sort of partial evaluator for passes. So if you have a pass and its input form, you could actually then generate, whatever is going to be generated out of it. Maybe that's an output form, but if you have a pass that's an interpreter, that can also be used to do things like Futomura projections as you're evaluating really into the code that you're going to generate at the end. So with all of that in mind, what do I really want? Well, I would like for there to be a language of Nanopass languages. So if we think back at our list of extensions, a lot of these extensions are things that could be very easily written if we had an API that was the language of our languages. So language arrow S expression, diff languages, prune language, define parser, define language node counter. All of these could be fairly easily written as a pass over a language that described the language. And we could imagine define language node counter, for instance, instead of even generating a function, which is a little bit complicated and needs to know some of the internals, it could simply generate a pass. And then the rest of the Nanopass framework could turn that pass into the function for doing the node counting. I'd also love to have a language for Nanopass passes. We could improve extensions like echo define pass so that we could actually have it print out the generated boilerplate code. And in fact, we might want to take the define pass macro, which is a fairly large and complicated macro, and apply sort of the Nanopass effect to it. So turn it into a set of smaller and more focused passes that are used to transform that into the final pass. Once you have these tools, though, it raises a question of why not write even more of the Nanopass framework using this? So how much of this could we actually write? We need some core pieces maybe for taking apart syntax, but once we have done that, couldn't we just write all of this using the Nanopass framework? So let's start by talking about an API for languages. Well, doesn't define language sort of already provide us a syntax? I mean, obviously we have a syntax that we're using, that we're decoding with syntax case in order to write our languages. But there are a couple of problems with it. The grammar is a bit messy. So language clauses are unordered. They can appear, the same clause could appear multiple times in some cases. Like for instance, we expect there to be multiple non-terminals. We don't necessarily expect there to be multiple terminals clauses, but we can support multiple terminals clauses. And some of the clauses, though, can only appear at most once. So our extends, for instance, obviously we don't support, I should say, extending for multiple different languages. And we can't have more than one entry specified for the language. So there are a handful of these that where the unordered clauses don't match really the grammar that we have. We have a pretty syntax for unparsers that I didn't show up front, but when we write this, it can use a non-S expression syntax. So we have this infix arrow operator here that's actually kind of nice to look at when you're looking at the syntax of these things, because it means that you can move all of them off to the side when you're reading the thing. But it's not a very schemely representation for this, and we probably don't want to try and pattern match over these things. Language extensions are also part of the grammar, and this is problematic for a couple of reasons. It means that if we were trying to parse the language as it was written by the user, we may have this extension that we have to deal with. We probably don't want to deal with the extension directly when we're writing most of these tools. And we also have to be able to parse our input potentially without knowing yet whether we have an extension or not. So we'd either have to do two-pass parsing, where we figured out if we had an extension and then reparsed the parts of the language that we weren't ready to parse, or we have to have some other way of handling this. And then finally, we have all of these references to terminals and non-terminals through our meta variables. Those meta variables are essentially some base plus some suffix. We already sort of have to go through the work of stripping off the suffix, figuring out and then figuring out which of the terminals or non-terminals it points to. It would be nice if that was something that the user of this system didn't have to do. So we'd like to avoid having to do these kinds of lookups and having to build this kind of lookup. So I want to take just a moment as a little bit of an aside and talk about the way the current Nanopass system works. The current internal structure, we have languages that are represented as collections of records. Not too surprising, we're building languages that are built out of records. We would just like to have these records, instead of being handwritten, be written as output to some language definition. At the base, we have a language. The language describes the sort of fixed parts of the language, what our entry point for the language is, the list of terminals and non-terminals. It also contains some information about the record structure of the language that we're building. So it has the record type descriptor and the record constructor descriptor for these things. Even though we never generate a record of the sort of base language, we have it there in order to have a language hierarchy where the productions inherit from the non-terminal that they belong to, and the non-terminals inherit from the language that they belong to. We have a T-spec record, which is used for describing terminals. It's the terminal specification. It has the initial name, the predicate, the meta variables, all of those are described in there. And we have a non-terminal spec. The non-terminal spec has the predicates and that are used for figuring out whether something is one of those non-terminals. That includes if we have terminals that are directly referenced inside that NT spec, those have to be captured inside those predicates. And we also want to capture sort of if we have non-terminals that are sub non-terminals of this non-terminal, we need to capture that in our predicates as well. It also has the meta variables used for representing the NT spec and the productions as well. We have a record called alt. If I was doing this today, I would have called it production, but these are basically the alternatives within our non-terminal specification, the productions. And so they capture a syntax, the base syntax of what was created, and then we actually have 3 derived record types. So we never create one of these directly, we create one of the 3 derived record types. Pair alt is how we represent the pattern. So when we have something like the quote pattern or the lambda pattern, those are represented by a pair alt, and they have the pattern, they have a separated out list of fields where we actually keep track of the nesting level of each of those fields if they have ellipses that follow them and that kind of thing. We also have what we call a terminal alt. This is basically when we have something like X or PR that shows up as a terminal that is in and of itself a production in the language. And we can also have non-terminal, bare non-terminals that appear in the language definition. This can be fairly common if we have a syntax where there's some kind of sort of decoration on top of some base non-terminal, where the decoration is optional. We might have a non-terminal that represents the decoration being there that has as a sub non-terminal the decoration not being there. And we'll actually see an example of that later. So the way all of this works, the language description record contains source, syntax, and it contains all this internal information along with it. The description can be used to generate record definitions, constructors, all the different parts. And that's why we have all of this internals stored within this. However, when we're actually looking to do something like language ARS expression, we usually don't need these internals. These internals are there for writing out what the record definitions are and writing out what our predicates are that we're going to expose to the user at the end. They're not really there for writing these kinds of higher level tools. So maybe we want our API to have both of these views. So I've said I'd like to use this to write the internals, but we may want a language for describing something that looks closer to the source structure. So something that looks a little bit more like the source structure, but addresses some of the concerns we had with just using the raw syntax, and then having an annotated version of the language that then contains all of this sort of gory details about the records and the predicates and the constructors and the accessors and the fields and the levels of the fields and all those kinds of things. Before we get into that, though, I'd like to take another slight aside here and talk about patterns in the language. So these are the patterns that we use for defining the productions of the language. We have a handful of them. We have a bare identifier. Remember that I mentioned at the beginning that the only location that we can have a sort of bare identifier that's matched exactly is that first position. So here, our bare identifiers are always a reference to a terminal or a non-terminal within our pattern. We can have maybe ID, which is an optional field. So we expect it to be a reference to a terminal or a non-terminal, but it'll either have the value type of that terminal or non-terminal or just be represented as #f. We can match null. We can match pair of patterns, X and Y. We can match a list of the pattern X, so we would look for 0 or more instances of things that would match that pattern. And then we also have this separate thing for matching where we have a list of the pattern X followed by 0 or more additional patterns followed by some sort of dotted improper list pattern here. And as I was working through all of this, I thought, this seems more complicated than it really needs to be. And in particular, as we look at this, these two guys at the bottom where we deal with dots, they seem like maybe it's overkill to have two separate pieces here. After all, X dots is really the same as X dots Y ... Z, where Y ... is a 0 length list of patterns and Z is just null, right? I mean, after all, we already have pairs in the language, and this is really just a variation on that pair syntax. So we can get rid of our dots, and now we're down by one whole pattern. That's great. We've simplified things a bit, but I think this is still more complicated than it needs to be. In particular, our X dots Y ... Z is pretty complicated, and as I was working on some of this stuff, I found it to be a pain to try and work with. And one of the things that I realized in looking at this, sort of suspected but needed to test myself, was that in fact, of course, because we have pairs in the language, we can already represent improper lists. And so really all we need is X dots and Y here, where dots is again our sort of S expression, is sort of our scheme syntax ... which we use for ellipses. So we can simplify this to just be a list of 0 or more of the pattern X followed by some Y. Maybe that Y is null. Maybe that Y is 1 or 2 additional patterns that are represented in a list ending in null. Maybe they're an improper list. We can support all of those forms with just this syntax. So this is our sort of final syntax on these things. It's much simplified from what we had to begin with. So getting back to the language API itself, I said that we wanted to have 2 languages out of this whole thing. So at the base, we have our simple language. Now, I know it doesn't look that simple. And in particular, I think in some ways it's maybe simpler than it should be, and in some ways it's more complicated than it should be. And I'll talk a little bit about that as we walk through the language. I suspect that some of this is going to change as I continue to evolve the design of all of this language API. Much of this stuff is very fresh. I just got some of this stuff working in the last week or so. So you'll have to bear with me a little bit on some of the bits and pieces here. Let's take a look at the terminals first. We have identifiers. Just as a note, we can't use symbols here because, of course, we want to be able to play nicely inside Scheme's hygienic macro expander. And that means that we have to hold on to the identifiers that we were originally given so that when we produce syntax out of these things, like in define language node counter, for instance, we're going to produce a pass that's going to operate over these things. We want to make sure that the identifier that we produce it with is going to have some of the same is going to have the same syntactic properties of the one that the user initially gave to us. So we can't just boil these things down to symbols. We also have what I call datum in here. Datum is really just, it could be any scheme kind of thing, any data type that can be represented in scheme. Oftentimes, I think this is going to be some syntax for something like a function or a reference to a function. But it could also be the function lifted into the syntactic environment itself. So we can actually produce a procedure that is actually a procedure at compile time and not just something that's going to eventually compile into a procedure. So this is gets a little complicated into the macro system, but because we have something like this, we want to be able to do this. We also have a box, and for those of you who haven't used Scheme or some of its sort of standard, non-standard extensions, box is really just what it sounds like. It's a mutable, it's a place where we can have mutable storage. So it's a single slot that we can side effect, we can put things into, and we're actually going to use that to make it so that we don't have to do lookups on our references. So when we have a reference, it's going to reference us back directly to the object type that represents that record. And so that's pretty handy for us to be able to do. We also have these things in here, dots and null. And we have these in here because we want a way to match ellipses, which are not something that we would normally be able to put in here, and null as literals. And we want to match them not in literal position, but in other positions within the language. I'll talk a little bit about more about that as we look at what the pattern looks like. So the language itself is very simple looking. We have defined language. It has the name of the language, and then it has our unordered clauses. This is one of those maybe too simple places. If we made defined language a little bit more complicated and fixed the position of our clause information, then we could have a little bit simpler time of actually dealing with the results. So here, the simplification in the syntax actually gives us a more difficult task in working with the language. The clauses that we have here are entry, which is the way that we specify what the entry non-terminal is for the language. Our list of terminals, of course, the non-generative ID. This is something that tools like ShaScheme use in order to make sure that we can bootstrap a compiler where we have a set of records that were produced for the compiler. We want to make sure that that same set of records with the same name gets created so that we don't have incompatible records created accidentally as we're trying to go through this compilation process for the compiler. So not something that I've used very often outside of ShaScheme, but it's handy to have inside tools like ShaScheme. And then we also have our non-terminal production here. ID is the name, ID star is the list of meta variables, B is the box that points back to this record actually, and then prod star ... is our list of productions. Of course, within terminal, we also have, or within our terminals list, we also have our terminals. A terminal is one of these non-terminals that has a non-terminal subtype in it. So a terminal is either a simple terminal or it's a terminal that's decorated with this handler. The handler can be used when we produce an unparser in order to give a pretty syntax for a terminal. And then the simple terminal is just the name of the terminal followed by the list of meta variables with, again, the box representing this record, which just in this case points back to the record itself. We also have our productions. So productions have a similar sort of structure. We can have a pattern. We can have a pattern with a pretty pattern, which will be used when we're unparsing if we aren't unparsing raw. We can have a pattern that has a function handler, which works similar to the terminal function handler. And then we have our pattern. And you'll notice that we have one slight difference in the pattern from the pattern that I talked about before, and that's because we're allowing identifiers, raw identifiers, to be used sort of anywhere in the language. So here, ID is just a raw identifier that's going to match a keyword. So, we might have a nested keyword within our system. Terminals is a good example of that in our language itself. We could have that be its own interior keyword with a system like this. Null is going to match our null. As I said, this is actually going to is in here so that we can match sort of the quoted null without having to specify it in the syntax here where it's not really allowed. We're going to have references. References are going to be references to either terminals or non-terminals. Maybe ref, which is a reference, an optional reference to a terminal or non-terminal. We have our pair pattern, pattern.pattern, and we have our dotted pattern, pattern 0 dots dot pattern 1. And then finally our references. References are either a terminal reference or a non-terminal reference. In the cases where it's a terminal reference, well, in both cases actually we have ID 0. This is the meta variable that originally appeared within the syntax that the user handed us. ID 1 is the name of that terminal or non-terminal. And then B is the box that contains the pointer off to the terminal that this represents or to the non-terminal that this represents. And so that's the simple language. We also have the annotated language. I know it looks more complicated, but in general, I think it's actually easier to work with, partially because of the ordered lists and because we've simplified terminals and non-terminals in a couple of ways that I'll talk about here. So our terminal list grew a bit. Record constructor descriptor and record type descriptor are scheme data types that are used for representing information about records. We also, in the internals of the language, we actually have a field that we use for numeric tagging. The numeric tagging is there so that we can do slightly quicker lookups when we're trying to figure out what kind of record we have our hands on instead of using the underlying record system. It's probably a vanishingly small performance advantage on each call, but if you do it enough, it's worthwhile. And so we have tag. We also have level, which is represents our nesting level when we've nested patterns within ellipses. And then we have tag mask. And the way we construct our tags is we have some representation that represents what the non-terminal part of the tag is, and then we have a separate part that is which production within that non-terminal it is, and the tag mask gives us a way to extract what that tag looks like. We've extended datum here. Probably most of these things that I've extended in datum, pred, all term pred, accessor, and maker, should all be moved into identifier. At the time that I originally wrote some of this stuff, I wasn't sure what types these were going to be. In particular, in the internal representation that currently exists, the all pred and all term pred are actually syntax for lambda expressions, as is the maker, I believe. And so these things are a little bit more complicated in there, and but I ended up not using them that way here. We also have our box, of course, and identifier, and then we still have our dots and null to support our patterns. So defined language got a little bit more complicated. It has an ID that represents the name of the language. It has a ref cell that represents the entry non-terminal. And then it has potentially a non-generative ID. It has the RTD, RCD, and tag mask for the language, a list of terminals, and a list of non-terminals. Each terminal has a sort of this simplified syntax here where we have the name as the ID, the list of meta variables, the box, and then optionally a handler if one was provided by the user, and the generated predicate. Non-terminals, similarly, we have the ID, the list of meta variables, or the name, the list of meta variables, the box, and then all the record information about it, as well as the predicate information. We don't need constructors here because we never construct these directly. And then we have our list of productions. The productions got a little bit more complicated and they reflect our internal syntax a little bit. So we have productions, which are pattern productions. They potentially have either a pretty pattern or pretty handler production. This is something that might change. I might just roll the maybe into the pretty production non-terminal here. They have also have a list of fields. And the reason why we separate out this list of fields is to make it easier for us to go through and actually process the results of extracting things from the language itself. And then we also have terminal and non-terminal, which are just references to the terminal and non-terminal, and potentially also have this pretty production. And then pattern and reference, these really haven't changed. They pretty much look the same as they did before. In fact, I think they're exactly the same as they were before. So that's our annotated language. So we've got our language API now. How well does it work? Well, as an experiment, I've created two new libraries, Nanopass Experimental and Nanopass Exp Syntax. Nanopass Experimental contains the languages and the passes for those language. It provides a function called lookup language, which can be called from within a macro. It needs to be passed the syntactic environment and the name of the language that you're trying to get at, and then it will hand you back that language record. The language record is a sort of record with two pieces to it. Language information language gives you back the simple language, and language information annotated language gives you back the annotated language, and then you can operate over those. Nanopass exp syntax is where I've stored the syntactic forms related to this. We need to store those separately because the way Scheme handles phasing, I didn't want to have to lift the meta level of all these functions that I was creating as passes, so I just put them in a separate library. And here I followed a naming convention that is pretty simple. I've added -exp to the names of all of the language-related syntactic forms. So we have, instead of defined language, we have defined language exp. Instead of language arrow s expression, we have language arrow s expression exp. Prune language becomes prune language exp, and etc. And I've done that for all of the language forms. Just to give you a feel for how some of this works, this is the actual syntax for defined language exp. You'll notice that this is a Shea scheme-ism here. Instead of returning a syntactic form directly from this defined syntax, I return a function. That function expects the compile time environment row as an argument, and then we use that for looking up languages when we have language extensions. Probably not too surprising to find that I actually have multiple passes in here with multiple languages, not just the two that we've talked about as the sort of results of all of this. So when we initially parse, we parse into something that's a little bit simpler, which I call LNP source. That simpler parsed language does not try and differentiate between extended and non-extended languages. That's handled in the next pass, which figures out whether we have an extended language or not. If we have an extended language, it gets the core language out of or the parent language out of the syntactic environment, figures out what the result should look like. We have a pass that then takes the results of that, whether it was a language extension or not, wires up the boxes so that we have our references set up properly, and also checks some basic stuff. So it makes sure that we don't have meta variables that overlap each other in different things and things like that. It's very likely that it should be doing a lot more checking than it actually does right now, but it's at least a start on that. Out of that pass, we produce our simple language, and then we annotate that language to produce our annotated language. And as I was working through all of this, I realized that I have a bug in there in handling the boxes because, well, mutable state, while it's convenient, is also a little bit evil. So hopefully I'll have an opportunity to address that shortly. But be aware that if you do try and use this stuff, the simple language boxes will point to the annotated language. You'll also notice here that I'm still expanding this into the core Nanopass defined language form. I'm doing that because I haven't written define pass or things like that yet. And so in order to test this stuff, I needed a way to actually define the core language and have things expand into passes that the core Nanopass language could expand for me into something useful. So how has the rest of this turned out? I've rewritten all of the language extensions as passes over languages. So I have defined language exp now, and I can define my languages. I can define all of the various extensions to define language that I had listed out before. I found that I often use the annotated language to avoid the unordered clauses, and I think that's an indication that probably the simple language might be better off with a little bit more structure in it so that we no longer have the unordered clauses. I also found that having patterns instead of sort of holding on to the syntax, it made a handful of things like language extension a little bit more complicated, but I think it also gives us the opportunity to do some things a little bit better. So right now, sort of syntax has to exactly match, and this would allow us to be a little bit more flexible and say, oh, well, I can see that that pattern is the same as this other pattern, even if you didn't use the exact same meta variable names. Producing syntax was relatively easy, although there are a couple of caveats, as there so often are when you're trying to play with syntax in as complicated a way as we are here. Sometimes we needed to use data mirror syntax. This is because, again, we're in a hygienic macro system. We sometimes need to break that hygiene in order to introduce identifiers that are going to match with the identifiers that the user initially gave us, which we stored within the language form. It's quite possible that instead of expanding into the syntax directly, what we really want to expand into especially when we're writing passes, for instance, is we might want to expand into some sort of pass syntax and then rely on something that knows how to expand pass syntax into something that looks like the correct syntax as a way of doing that job for us. So that's great. What about an API for passes? Well, we need a language for passes, but I haven't quite gotten to this yet. As I sort of mentioned, a lot of this stuff is very new. I didn't quite have enough time to do everything that I wanted to do before my presentation was due, so this is future work. But let's talk a little bit about the plans for what that work looks like. So we have some future direction here. The obvious next step is, as I mentioned, we want to create a language of passes. So I've already started actually implementing a language of passes. It's a little bit more complicated because there are places where we just have potentially large blocks of scheme syntax. In our clauses, we can have just random scheme syntax in there, and we need to make sure that we sort of can handle that in a way that is still useful for doing this stuff. But with that caveat, implementing the languages is not too difficult. I think implementing define pass exp is going to be a little bit more involved, but I think it's fairly straightforward. I think it's mostly just work. So we need to implement the meta parser for matching and construction because we can no longer rely on the core Nanopass system for doing those things for us. We also need to re-implement the boilerplate generation code as a pass. So we have that code obviously as part of the larger define pass macro right now, but it's going to need some refactoring in order to deal with the fact that it's now handling passes. Overall, I think this is actually an opportunity to improve things. And so there are places where we don't generate quite the code that we would like to generate. And that either leads to us writing more code than we wanted or writing the code in a slightly different way so that we can take advantage of the boilerplate stuff. And so I think we can improve some of that stuff. So the experimental language and pass are really only a start to this future direction, though, because they are still going to rely on the original, the current Nanopass framework in order to work. And so we need a way to sort of partially evaluate these things to produce a language core. You might think of this as sort of like a compiler bootstrapping. So we need to have the basic core of the compiler available for us so that we can produce sort of the rest of the results. The idea here is to keep it as light as possible. I think keeping it as light as possible is part of the challenging part. So we don't want to generate, say, for instance, a JScheme library that you have to load in order to do anything else with the Nanopass framework. We'd like to make sure that we still have sort of R6RS compliant syntax that you can pull in, at least if you're using an implementation with the portable syntax case. So we want to keep that to something where it's approachable and usable and generally not a big pain to try and pull down and use. So just to wrap up a little bit, the language experiment seems pretty promising. As I mentioned, it has a couple of bugs, and I think there are some improvements that need to be made for some of the syntax, but we've got a good start on this, and it seems to be working. I actually did some sort of quick shaking out pass testing by using it for a little compiler that I'm going to talk some about tomorrow. But this is basically gives me a little bit of confidence, at least, that some of these bits and pieces have been tested a bit. The pass experiment seems relatively straightforward, even though I think it's a fair amount of work. And I'm hoping that the core can be generated from this source and that we can keep it all fairly light. All of this is something that you can try out today. So I have checked in my changes into the main Nanopass repo. Because these things are in separate libraries, they don't impact any of the sort of core parts of the language, so you can pull those down and use them. And with that, I just wanted to say thanks again. Appreciate everybody's attention and being invited to do this. Hopefully it was interesting for you. And I'm happy to take any questions on the chat. And so I think now all of that is happening on the Twitch chat. And hopefully I am still awake. I'm about 9 hours off from the rest of the conference, but my plan is to be sitting at the keyboard while we're doing this. So I will see you there.